any polynomial. One other thing, we found zeros of polynomials, but sometimes zeros get what are called repeated, and they're called repeated roots or zeros. So what we're going to talk about next is repeated roots or zeros. So before we talk about that, let's talk about something like this first example, y equals x squared minus 4. We find out it's zeros by factoring it. This x squared minus 4 factors as an x plus 2 and an x minus 2, which is equal to 0 when x equals negative 2 and x equals positive 2, which is why that's where you cross your x-axis. That's when you're equal to 0, is at negative 2 and positive 2. Now notice that they both have, that they're both to the first power. That's why they're going to be considered what's called multiplicity of 1. Because they only occur once, and because they're raised to the first power. So we'll call that a multiplicity. Multiplicity of 1. So what happens if we have something that isn't a multiplicity of 1, let's say a multiplicity of 2? Well, first of all, multiplicity of 1, we saw what happens. It just cuts through the x-axis at that value, either going up or going down. So multiplicity of 1 means that you just cut straight through the 0, because it's raised to the first power, that root, or 0, or x-intercept, whatever you want to call it. However, if you have something like an x plus 2 squared, then we're talking about a multiplicity of 2, because it actually has a squared on it. It happens twice. And when we say even multiplicity, it could be squared, 4th power, 6th power, anything that is actually even. And what happens when you have a root with an even multiplicity is it doesn't actually cut through the x-axis, it actually just bounces right off. Wherever your intercept is, if your multiplicity is even, you'll bounce off the graph. Sometimes you'll bounce off the graph from up top, sometimes you'll bounce off the graph from on the bottom. Okay, what if it doesn't have a multiplicity of 1? Doesn't have an even multiplicity, but has, let's say, something that's still something different, something odd. So what if we had, like, let's say an x plus 2 to the 3rd? That's odd, but it's not 1. So it does still just cut straight through, but it doesn't cut through at a straight line like it did if it's raised to the first power. The first power is special because it is, when anything's raised to the first power, you're dealing with something linear. That's why it cuts through at a line for if you have a multiplicity of 1. However, if you have an odd multiplicity, meaning something cubed to the 5th, to the 7th, anything like that, anything that's not 1 but is odd, what you'll do is you'll kind of make almost like a little mini cubic graph, which means you'll kind of do that snake shape, going up or going down through your root, whatever it was. So you'll still just cut through the root, but it won't be a line. It will be kind of like a cubed snake graph, like what we saw earlier in this course. Even if it's to the 5th power, 7th power, it'll kind of look like that. It will just be more and more exaggerated the higher the exponent. So the point now that we want to get into is now putting all this together so that we can graph some generic polynomial the best that we can. So the first thing that we want to do is break our polynomial up into factors. The hope is that it factors, but if not, we can always use our synthetic division. The second part is to make sure that we know all of our multiplicities and how that's going to affect. So again, if we factor, we'll be finding our zeros or x-intercepts first. Then we'll go after their multiplicities. Then we want to look at plugging in 0 for x. because what that will do is tell us when we intersect the y-axis. In step 1, we actually already found the x-intercepts. Now we're finding the y-intercept by plugging in 0 for x. Then we want to talk about the end behavior of the graph as well, meaning what's happening at the ends. Are they both pointing up? We just did this. Both pointing down, if we're dealing with an even function, or is one up and one down, or is one down and then one's up? We need to figure that out. The last thing is, once we've figured out the end behavior and we've filled in our zeros, we have our y-intercept, we have all of our x-intercepts, is to figure out, and we have our multiplicities, we need to test some values. So what will happen is we've created an interval of values and we'll need to test in between them. And that's what I always do at the very last. And then what we'll do is, once you have all those steps completed, we need to fill in the graph. But it should be pretty much there. We'll just have to kind of play connect the dots and follow our arrows, and you'll see what I'm talking about in just a little bit. One last comment before we get to an example is about turning points. Turning points are where you change from increasing to decreasing. And the idea is, if you have a polynomial of degree n, which, remember, the degree is the highest exponent, then it can at most change directions one less time than your degree. So let's say if your exponent is a 5, at most you can switch from increasing to decreasing one less than that 4 times. If your degree is, let's say, 6, you can only change direction, let's say, one less than that, which would be 5. That's how many times at most. It doesn't mean that you will definitely change direction that many times, but that's what you can do at most is the key. So that also gives you an idea. And where you change direction from increasing to decreasing is called a turning point. Let's take a look at this first example. In this first example, they've actually done a lot of the hard work for us by factoring this for us. So the first thing that we're going to look for is our x-intercepts / our zeros, which means we're going to take our little factored polynomial and set it equal to 0. And what we'll notice is that it's equal to 0 when each of the pieces are equal to 0, which means when x equals 0, this first piece, and when the second piece equals 0, the x plus 2 equals 0, which, subtracting 2 to both sides, will give us x equals -2. So we've got 2 zeros so far. We have one more to deal with, which is when x minus 2 equals 0. And adding 2 to both sides, that will get us a +2. So that gives us our 3 zeros here. And the reason why we're getting 3 zeros, if you go back up to the top, is that we have an x times an x times an x, which means our highest exponent is an x cubed. Now notice these are all 1x's. So when you multiply them together, you'll still have a 1x cubed. Don't really care about what the rest of the terms are if you were to FOIL everything out. So we're just going to stop there. But we do need to know what this first term is, and we will use this in a little bit. Continuing along, so we have our 3 zeros. What we're going to now do is put these on kind of a mock-up. So we're going to put it on a number line to at least get us started before we do our final graph. We need to put them in order. The smallest value that we found for our zeros was -2. Then we found 0, and then we had +2. Those were our zeros, so that's where we're going to cross the x-axis. We cross the x-axis at 0 and at -2. And at +2. Okay, continuing along, let's see what's going on here. We also know that each one of these had an exponent of 1 on them. X to the first power, this thing had a hidden 1 and a hidden 1. So what that means is all of these had a multiplicity of 1. which means that when we cut through these zeros, they'll cut through at just a line. So, but let's go ahead and just get used to doing this and writing it out so that we're in that habit. Okay, next thing that we care about is the end behavior.